Now let's discuss time evolution in quantum mechanics. So far we discussed the fundamental features of time evolution in classical mechanics. Okay, so we saw that time evolution equations are deterministic and they are reversible in classical mechanics. All right, and we also saw that the reversibility is clearly seen from Liouville's theorem. Right? Now, with that introduction, let's move on to time evolution in quantum mechanics. We'll start with uh, what we mean, how we represent time in quantum mechanics. Okay, so the important point that we should keep in mind is that time is just a parameter in quantum mechanics. Right? We saw that position is an operator, momentum is an operator, but we'll treat time as a parameter only, which means that time is not an observable. Right? We don't treat time as an observable. In other words, we don't have a time operator like we have a position operator. We have a position operator, we have a momentum operator, but it doesn't make sense to talk about a time operator in the same way. So we'll treat time as a parameter just like in classical mechanics. All right. In other words, time and space are not treated symmetrically in quantum mechanics. In other words, we are going to learn non-relativistic quantum mechanics, right? Because in relativistic theory, space and time should be on equal footing. They should be treated symmetrically. So clearly, we see that in the quantum mechanics we are going to learn, time and space are not treated symmetrically. Later, you will learn that there is a successful relativistic quantum theory. Right? This is called quantum field theory. And in quantum field theory, of course, because it is constructed to be a relativistic theory, in quantum field theory, you will treat space and time on equal footing. All right. But for that, what we do is that we don't make time an operator. Instead, we'll make position also a parameter. So in quantum field theory, you will see that position and time will be treated as parameters. All right. Okay. So in what we are going to learn, time is just a parameter. The time evolution operator. The basic question that we try to answer in this section is, how does a state get changed with time? That is, suppose we have a physical system whose state get at some time t0, where the state get is represented by get alpha. So this is the state of the system at an initial time, say at time t0, right? Now, of course, generally things change with time. So at a later time, we don't expect all states to remain the same. We expect the state to change with time. Okay. So at later times, we do not in general expect the system to remain in the same state represented by get alpha. Let's first fix the notation. We said that the state of the system at time t0 is given by get alpha. We shall denote the get corresponding to the state at some later time by get alpha comma t0 semicolon t. So this t means that we are talking about the state of the system at time t. This t0 alpha comma t0 is used here to specify that the state of the system at time t0 was get alpha. Okay, so this t0, we have written alpha comma t0 inside the get here to remind ourselves that the system used to be in state get alpha at some earlier reference time t0. So this is the notation that we shall be using. Now we know that time is a continuous parameter. We shall assume that it is a continuous parameter also in quantum mechanics, which means that we can take arbitrarily small values of t. Okay, we can take the limit t tends to t0. So in the limit where t tends to t0, we should get back the same state get alpha, because get alpha was the state of the system at time t0. Okay, so we can use a shorthand notation like this. Get alpha comma t0 at time t0 is equal to get alpha comma t0. Right? We don't have to write this t0 for the case where t equal to t0. Right? So get alpha comma t0 at time t0 can simply be written as get alpha comma t0, where t0 is the initial reference time. Okay. So this is our basic task. We have got the state of the system at time t equal to t0, which is written as get alpha. So this is the state of the system at some initial reference time t equal to t0. After a time evolution, all right, after some time, the state changes to another state. Let's call this state as get alpha comma t0 at time t. Okay. So our question is, how are these two states related? on the one hand we have got get alpha at time t equal to t0. On the other hand we have got a state get alpha comma t0 at time t. Okay, how are these two related? So we have got two states. How are these two states related? Okay, now we know that operators relate different states. So actually we are looking for an operator that relates the states get alpha and get alpha comma t0 at time t. Okay, what kind of operator relates these two states? Now let us assume that there exists an operator that relates the two states, the state at an earlier time get alpha, okay, and the state at a later time, which we denoted as get alpha comma t0 and time t. Okay, we can call this as the state at time t. Okay, whose initial state was, or whose state at time t0 was get alpha. So here is the state at the later time, the time evolved state, get alpha comma t0 at time t. Okay, and this is obtained. We assume that there exists an operator which we denote as u of t comma t0, which takes the state or which changes the state from get alpha comma t0 to this new state, right, to the state at a later time. So we just use this notation for this operator, which we can call the time evolution operator. Okay, we'll write it as u of t comma t0. We have written it as in such a way that it has two arguments. One is the initial time and t, and the other argument is the later time. Okay, so we say that u of t comma t0. So we say that u of t comma t0 acts on the state at acts on state at t0 and takes it to the state at some later time t. Okay, so these two arguments, one of the arguments stands for the initial time and the other argument stands for the final time. Okay, now we have just written an equation that relates two gets, an operator equation, or sorry, a relation that relates two gets, the get at an initial time and the get at a later time. Okay, we don't know much about it, but if we start with such a time evolution operator, we shall call this the time evolution operator. If we start with such an equation, okay, are there some properties that we would like this operator to have? Okay, are there some properties that we would like this time evolution operator to have? And as we said, here is where this ideas from classical mechanics comes in. We know that in classical mechanics, right, the equations of motion or the time evolution equations were deterministic and reversible. In other words, we had conservation of information. All right. Now it was a very successful paradigm, and we would expect that something like that holds also in quantum mechanics. Right. So we would expect. So we can, what do you say? We can ascribe some conditions or some properties to this operator in such a way that this time evolution is both deterministic and reversible. Okay. So just as in classical mechanics, we shall require that the time evolution is such that information is conserved. That is, the time evolution can be expected to be deterministic and reversible. The next question, of course, is how do we formulate this mathematically? Okay, how do we demand that the time evolution is in such a way that information is conserved? All right, so that is, we have the time evolution operator, which we denoted as u of t comma t0. We have certain properties that we would like this operator to have. We said that this operator should be in such a way that information is conserved. The question is, how do we demand this mathematically? How do we demand the requirement that information is conserved? How do we demand this mathematically? Okay, it can be seen that information will be conserved if the normalization is preserved under time evolution. Okay, what do we mean by normalization is preserved? Right, this means the following. Suppose the state at time t0 is get alpha, and we are usually using normalized states. So let's say that bracket alpha is equal to 1. Now our claim is this. Okay, conservation of information implies that bracket alpha comma t0 at time t, alpha comma t0 at time t is also equal to 1. Okay, so if the state is normalized to 1 at the initial time, we are requiring that the state is normalized at a later time also. In other words, the normalization is not changed by time evolution. Okay, so again, this is the claim: conservation of information. Conservation of information implies preservation of or conservation of normalization. Okay, of course, you may ask, what does the conservation of normalization uh, have to do with conservation of information? What's the relation between conservation of information and preservation of normalization? Okay. This can be understood easily based on the probability interpretation in quantum mechanics, or the probability postulate in quantum mechanics. Now consider a state ket alpha that is normalized to 1, which means that we can write bracket alpha, alpha is equal to 1. Right? We know that we can always normalize a state by multiplying it with a number, because multiplying a ket with a number does not change the state that it represents. We have seen this in the first chapter. Now again, as usual, let's expand this ket in terms of the eigenvectors of an observable A. We said that a Hermitian operator has eigenvectors that form an orthonormal set, and you can use the eigenvectors of a Hermitian operator as the basis. So we can expand this ket alpha in the basis formed by the eigenvectors of operator A or observable A. Okay, these are the expansion coefficients. These are the complex expansion coefficients. Now, we have also already seen that the normalization of the state means that the quantum mechanical probabilities for various possibilities add up to 1. Okay, so I think we have we have already seen this. If bracket alpha, alpha is equal to 1, you just put it, you just use alpha, ket alpha is equal to sum over a prime ca prime ket a prime, and this condition boils down to sum over a prime modulus ca prime square is equal to 1. Okay, and what was modulus ca prime square? According to the probability interpretation, this is the probability for measuring an eigenvalue a prime of the observable A. Okay, so P of A prime is equal to modulus C A prime square if bracket alpha, alpha is equal to 1. If this is not equal to 1, then this is also not true. But if this is normalized to 1, then we can interpret the modulus square of these expansion coefficients as the probabilities for various measurement outcomes. Okay. So this statement just means that the sum of all probabilities add up to 1. And this is why the normalization is important for quantum mechanics. That is, bracket alpha, alpha equal to 1 implies that sum over a prime modulus c a prime square is equal to 1. Of course, if you don't remember how we did this, please stop here and check this. All right, you can start with get alpha equal to sum over a prime c a prime get a prime. The corresponding bra or bra alpha can be written as sum over a double prime c a double prime star bra a double prime. Okay, take the inner product, use the orthonormality condition, bracket a prime a double prime is equal to delta a prime a double prime. Okay, and then you see that it will lead us to this equation. All right, so bracket alpha, alpha equal to 1 will give you sum over a prime modulus c a prime square is equal to 1. Okay, so this normalization just means that the probabilities of all the possibilities, if you take the probabilities for all possibilities and add them up, you should get 1. Okay, now let's talk about the conservation of normalization. All right, now we have interpreted these expansion coefficients or the modulus square of the expansion coefficients as the probabilities. Okay. Now the normalization, the value of normalization actually tells us that probabilities add up to 1. All right. Now since these are the probabilities, they cannot add up to a number greater than 1, because if you add all the probabilities, it should give you the maximum it can have is the value 1. Okay, so since these are the probabilities, at a later time, the probabilities cannot add up to a number that is greater than 1. All right, so for this reason, it's clear that the inner product, all right, bracket alpha, alpha, cannot exceed 1. It cannot be greater than 1 at any time. Okay, so if bracket alpha is equal to 1, since these expansion coefficients are related to the probabilities, this means that bracket alpha comma t0 at time t, alpha comma t0 at time t cannot exceed 1 at any time, because if it exceeds 1, that would mean that the probabilities add up to a number that is greater than 1, and that does not work. Okay, so if the probability postulate is correct, or according to probability postulate, this inner product cannot exceed 1 at any time. All right, can it be less than 1 at any later time? That's what we'll examine next. Now, it can easily be seen that if initially the probabilities of all possibilities add up to 1, it cannot decrease either. For example, suppose that after the time evolution, all right, so initially we have bracket alpha equal to 1. Now, suppose after the time evolution, we have bracket alpha comma t0 at time t, alpha comma t0 at time t is equal to half. For example, right, let's consider this example. Suppose initially the normalization is 1, and at a later time the normalization has dropped to half. What does this mean? This means that when we started with get alpha, the probabilities over all possibilities added up to 1. All right, so get alpha contains the information regarding all possible measurement outcomes at an initial time. Okay, that's why the probabilities add up to 1. Right, now suppose this has dropped to half. This means that the probabilities of various possibilities included in get alpha comma t0 at time t has now dropped to half. Okay, which means that get alpha comma t0 at time t does not now contain the information of all possible measurement outcomes. All possible measurement outcomes. Okay. In other words, information wouldn't be conserved. All right. So I'll repeat this argument. If bracket alpha is equal to 1 initially, this means that the probabilities over all possibilities add up to 1. In other words, get alpha, specifying get alpha, has the information of all the possible measurement outcomes. All right. But if the normalization later, or the normalization drops to half, this means that at a later time, the time evolved state does not have the complete information regarding the system, because the probabilities have dropped to half. There's a 50% probability that the there's a 50% probability for any other possibility which is not included in this time evolved state, which means that we have lost information. Initially, we have complete information in the state get alpha. At a later time, we have lost some information, right? We know only about half of the, we only know of half of the possibilities, right? The rest of the possibility, the information regarding rest of the possibilities is not now included in the time evolved state. Okay, so if we want information to be conserved, or if we want time evolution to be deterministic, then we must also have bracket alpha comma t0 at time t, alpha comma t0 at time t equal to 1. Okay, so again, if the normalization has dropped to 1, dropped to half, this means that this would mean that the final state is not completely determined by the time evolution equation given the initial state. Right, so we are given the initial state. Okay, the final state, right, all the information regarding the final state is not determined given the initial state if the normalization drops to a lower number. So normalization cannot drop to a lower number if we want determinism, or if we want conservation of information. Okay, so for deterministic time evolution, we may demand that normalization is conserved. Okay, we talked mainly about determinism. Let's now look at reversibility. Following Liouville's theorem in classical mechanics, we may demand that distinctions are also conserved, because if a time evolution equation is to be reversible, the distinctions must be conserved under the evolution. Right? The different states must evolve into different states in the future. Now, for time evolution to be reversible, distinct initial states must evolve to distinct final state, as we said. Now, we have seen that orthogonal states correspond to distinct measurement outcomes. Right? We have already discussed this. Okay? Orthogonal states represent states corresponding to mutually distinguishable or mutually exclusive measurement outcomes. We have talked about this. So the conservation of distinctions means that the states that are orthogonal initially must remain orthogonal at all times. Right? Again, suppose we have got two states, ket A prime and ket A double prime. All right, they correspond to different measurement outcomes of observable A. We know this. These are because the eigenkets corresponding to different eigenvalues are orthogonal. We know this, and they correspond to mutually distinct measurement outcomes. Okay, we know that bracket A prime, A double prime is equal to 0. All right. Now this must be true also at a later time. This means that bracket A prime comma T0 using our notation at a later time, A double prime comma T0 at a later time. This also has to be 0. So if distinctions are to be preserved, orthogonal states must remain orthogonal even after time evolution. Okay. So this is reversibility condition. Now we can show that these requirements of determinism and reversibility imply that the time evolution operator is actually unitary. Right? This is what we are going to see. Right? If you need the normalization to be preserved or the orthogonality to be preserved, this means that the time evolution operator has to be unitary. You have already seen unitary operators. If an operator is unitary, it means that u dagger u is equal to u dagger is equal to the identity operator. This is unitarity. So let's see how a requirement leads to unitary condition. Okay. So let's start with the conservation of probabilities. Again, suppose that at T0, a state get is expanded in terms of the eigenkets of some observable A. Right? So we write the initial state is expanded in the basis of the eigenkets of operator A. All right. So we are careful here. We'll write this as get alpha comma T0 equal to sum over A prime C A prime of T0 get A prime. Okay. Now we have got the state at a later time. This state is also expanded in the same basis. Right? This state we are expanding the time evolved state or the state at a later time also in the same basis. Right? The basis has not changed. We are just expanding two different states in the same basis. Okay. So since the basis vectors are the same, we expect the expansion coefficients to be time dependent or expansion coefficient to be different. All right. So here we write the expansion coefficients as Ca prime at time t0 or simply Ca prime of t0. Here we write the expansion coefficients as Ca prime of t. Okay. Now we want the normalization to be conserved. In other words, we want the sum. This is what we require. Sum over A prime Ca prime of T0 modulus squared has to be equal to sum over A prime modulus square of Ca prime of T. Okay, this is what we demand. Now, of course, this will be satisfied if the modulus of the expansion coefficients do not change. Right. So one way to make sure that this is possible is to demand that modulus Ca prime of T0 is equal to modulus Ca prime of T. And this is one way to satisfy this requirement, right? But of course, we don't expect this to happen because there are simple physical systems which show that the individual expansion coefficients actually do change with time. All right. For example, let's consider a spin half system with its magnetic moment subjected to a uniform magnetic field in the z direction. All right. So we have got a uniform magnetic field in the z direction. All right. Now let's consider the initial state to be get Sx plus. Okay, let's consider the initial state at time t0 to be get Sx plus. Okay, that is our get alpha in this case is simply get Sx plus. Okay, so suppose that at time t0 the spin is in the positive x direction, that is the system is prepared in an eigenstate of Sx with eigenvalue h bar by 2. Okay. Now it's easy to prepare. You just pass the beam to an through an SGX head apparatus, and then you block one of the possible outcomes. All right, you just block the get Sx minus beam, and what we have here is get Sx plus beam. Okay, so we can use the atoms from this apparatus. right? This is, you can call it as an Sx plus filter. So we can use the atoms from an Sx plus filter. Okay, so we have got get Sx plus as the initial state. Now, as time goes on, we can see that the spin precesses in the xy plane. Right? It doesn't stay the same, it just rotates in the xy plane. This can also be seen theoretically, which we will do later in this section. For now, we just take it as an experimental fact that the spin precesses in the xy plane. Right? This means that initially we would have Sx minus Sx plus is equal to 0. But at a later time, we would see that get Sx minus Sx plus, right? Let me put it like this using our notation Sx minus comma T0. Sorry, this is the basis vector. So bra Sx minus get Sx plus comma T0 at a later time T. You see that this is not equal to 0. Alright, so it can actually be seen experimentally that even though get Sx plus has no component along the Sx minus direction initially, alright, because of this rotation, later it picks up a component in the get Sx minus direction. Alright, so this is what we have initially. Initially, we would have the individual expansion coefficients like this. Bra Sx plus get Sx plus is equal to 1. Okay, this is initially. All right, and bra Sx minus get Sx plus is equal to 0. This is the initial state. All right, these are the initial expansion coefficients. At a later time, we are saying that bra Sx plus get Sx plus comma T0 at a later time is less than 1, all right, and bra Sx minus get Sx plus comma T0 at a later time is now greater than 0. All right, but it can be seen that these probabilities add up to 1. I should put a modulus here because we are talking about the probability, so better we can put a modulus square. That's better. All right, so we see that this probability now becomes less than 1, and this probability now becomes greater than 0. But the sum of the probabilities remains to be 1. Right, the sum of the probabilities remain the same. So what we have is, initially we have got a get Sx plus state, and later it picks up a component along, it changes, all right, it evolves in time, and it picks up a component along the get Sx minus direction also. So total probabilities do not change, but the individual expansion coefficients can change. All right, so for the conservation of normalization, we don't demand that individual expansion coefficients remain the same, or the modulus of individual expansion coefficients remain the same. All right, this we cannot require. Okay, because experiments show that this is not the case in all situations. All right, there can be certain situations where this is the case. Indeed, we'll see some situations like that, but this is not generally the case. Okay, so even though we don't have modulus Ca prime of T0 not equal to modulus Ca prime of T, we still must satisfy this condition. Sum over A prime modulus Ca prime of T0 square is equal to sum over A prime modulus Ca prime of T whole square. Okay. Now what is this? This is simply the inner product, or this is simply bracket alpha alpha. What is this? This is simply bracket alpha comma T0 at a later time T, alpha comma T0 at time T. Okay. So this equation is simply the demand that bracket alpha comma T0, alpha comma T0 is equal to 1, means that bracket alpha comma T0 at a later time, alpha comma T0 at a later time T is equal to 1, or normalization is conserved. Okay. So the probability postulate, along with the demand that the time evolution is deterministic, gives us this condition, all right, that the normalization is conserved even though the modulus of individual expansion coefficients can change. Okay. Now this property is guaranteed if the time evolution operator is taken to be unitary. All right, because we said that this is how we represent time evolution. Get alpha comma T0 at time T is equal to u of T comma T0 acting on get alpha comma T0. Okay. So this means that bra alpha comma T0 time T is equal to u dagger. I should write like this: bra alpha comma T0 and then u dagger of T comma T0. All right. Now, if we demand that bra alpha comma t0 at time t, sorry, bracket alpha comma t0 at time t, alpha comma t0 at time t is equal to bracket alpha alpha. This means that now we can just substitute these two in here, right? These two in here, because bra alpha comma t0 at time t is written as bra alpha comma t0 u dagger, all right, and get alpha comma t0 at time t is written as u acting on get alpha comma t0. Okay, so the conservation of probabilities or the conservation of normalization means that bra alpha comma t0 u dagger u get alpha comma t0 is equal to bra alpha comma t0 get alpha comma t0. Okay, which means that this u dagger u in here has to be the identity operator. Okay, this implies that u dagger u is equal to the identity operator. All right. So based on conservation of normalization, we say that the time evolution operator must be a unitary operator. Okay, this is a fundamental property. This is one of the fundamental properties of the time evolution operator, that it has to be unitary. Okay, I hope this is clear. So we have seen that unitarity of time evolution guarantees conservation of distinctions and hence automatically satisfy the reversibility criterion too. Why? Because if you have two states which are initially orthogonal, all right, if this is the case, then we know that ket A double prime will go to U acting on ket A double prime, and ket A prime will go to U. Sorry, I'll write it like this. Bra A prime will go to U dagger. Sorry, bra A prime U dagger. Okay. So if bra A prime comma A double prime equal to 0, if we want this to be conserved, we will get the condition bra A prime U dagger U get A double prime is equal to 0. Okay, this again means that U dagger U is equal to 1 for the identity operator. All right. So unitarity automatically guarantees the conservation of distinctions also. All right. In fact, right, it's clear that if the time evolution operator is unitary, then all inner products are conserved. Right? All inner products are actually conserved. This could be true for any state. Bracket alpha beta will become equal to, right? So let's say that ket alpha goes to u acting on ket alpha, not equal to, goes to, and ket beta goes to u acting on ket beta. All right. This means that bracket alpha beta is equal to bra alpha u dagger u, it's not equal to, goes to bra alpha u dagger u ket beta. Okay, this is equal to, if this is unitary, this is equal to bracket alpha beta. Okay, so you see that the inner products are preserved under unitary time evolution. All right, so in general, the inner product between any states is conserved under unitary time evolution, and one could call this the conservation of overlaps. Okay, so we say that, so this bracket alpha beta is actually the component of beta along alpha, right? Or it's the overlap between these two states. So in general, we can say that the amount of overlap is also conserved. Right? The amount of overlap is also conserved. Right? In other words, the logical relation between the states is conserved under unitary time evolution. Okay. See, if a state has a particular amount of overlap along another state, this amount of overlap cannot change. This amount of overlap cannot increase. The amount of overlap cannot decrease. It remains the same. Okay. In other words, the basic logical relation, between the states is conserved. Now, this is very similar to what we saw in Liouville, what we saw in when we discussed Liouville's theorem of classical mechanics. All right, over the distinctions are preserved. All right, not only are the distinctions preserved, they don't merge together. Right, the time evolution do not bring the trajectories closer. All right, in the same way, in quantum mechanics, provided the time evolution operator is unitary, the logical relation of the overlap between states does not change. All right. So we can say that unitarity in quantum mechanics is actually analogous to what Liouville's theorem states about time evolution in classical mechanics. All right. So unitarity in quantum mechanics is analogous to Liouville's theorem in classical mechanics. All right. So the conclusion is the time evolution operator. We defined the time evolution operator like this: alpha comma t0 at time t is equal to u of t comma t0 acting on get alpha comma t0. All right. This is how we define the time evolution operator. Now, based on based on conservation of information, we concluded that this operator must be unitary. U dagger u has to be equal to 1, right? Or u dagger u is equal to u dagger has to be equal to 1. Actually, to be precise, we have not proved this part, but I think we'll be doing that later. Okay, so what we have seen is that u dagger u has to be equal to 1. Okay, now we can try to prove that if u dagger u equal to 1, then u dagger also has to be equal to 1. Maybe we'll be able to do that later. So the basic idea is that the time evolution operator has to be a unitary operator if we need conservation of information. Okay. So the conservation of normalization is guaranteed if the time evolution operator is taken to be unitary. So we take unitarity, u dagger u is equal to 1 to be one of the fundamental properties of the time evolution operator.